As we have compared boiling and evaporation, let us now focus on boiling in detail. What do we mean by boiling phenomenon? What are the different stages in boiling? Boiling is basically rapid formation of vapor bubbles at solid liquid interface where the solid temperature is higher than the liquid saturation temperature. There are bubble formation, and these bubbles of the liquid detach from the surface when they reach a certain size and attempt to rise to the free surface of the liquid. This is a form of a convection heat transfer as shown here. This is the heating element, and there is bubble formation which rise to the top of the liquid surface, and we have this T saturation of this liquid is at 100 degrees centigrade, and the temperature of this heating surface is above 100 degrees centigrade, that is about T saturation. So boiling heat flux from a solid surface to liquid is expressed from the Newton's law of cooling as Q boiling is equal to H into the temperature gradient, but here the temperature gradient is between excess temperature of the heating surface and the T saturation temperature of the liquid. So the temperature of the surface should be higher than the saturation temperature of the liquid at that pressure is basically the requirement for boiling. Boiling, as we know, is basically of two types. There is pool boiling and there is flow boiling. Pool boiling is basically in the absence of bulk fluid flow. As you can see here, within pool boiling there is no bulk fluid flow. The fluid is stationary and it is in contact with a surface that is at a temperature higher than the saturation temperature. Whereas in flow boiling there is presence of bulk fluid flow as shown here. There is heating carried out and the fluid is also flowing as the bubble formation is taking place. Pool and flow boiling are further classified as subcooled boiling or saturated boiling. In subcooled, or which is also referred to as local boiling, the temperature of the main body of the liquid is below the saturation temperature Tsat. That is, the bulk of the liquid is subcooled, whereas in saturated or bulk the temperature of the liquid is equal to the saturated, that is, the bulk of the liquid is at saturated temperature. So this is the difference between subcooled boiling and saturated boiling. Boiling takes different forms, and these different forms or stages depend on the value of the excess temperature of the surface, which is basically higher than the saturation temperature. Depending upon what the excess temperature is and how the boiling process takes place, boiling regimes are observed, as you can see in this phase change diagram. The first is natural convection boiling, which is observed in the earlier at a lower T excess or delta T excess. As the delta T excess increases, we observe nucleate boiling. After that, we observe transition boiling at higher delta T excess. Delta T excess is basically the temperature difference between saturation temperature and the surface temperature. And then we observe film boiling at the highest delta excess points. So now we will discuss these in detail. As you can see here, as we go on, first at lower temperature difference, that is the surface is basically at 103 degrees centigrade and saturation temperature is 100 degrees centigrade. So delta T excess is about 3 degrees centigrade, and we have heating and we have natural convection boiling. After that, we have the nucleate boiling, formation of bubbles. They are getting detached from the surface and move up in the upper region of the fluid. As the T excess here has been increased, the surface temperature has been increased to 110 degrees centigrade. After that, we have transition boiling, where we notice that there is vapor pockets that are formed because now the T excess is very high, and here the T excess is about 80 degrees centigrade, as you can observe. And then we have a complete surface which is covered by a vapor film, and this is called as vapor film or film boiling, and we have a T excess very high, about 400 degrees centigrade here. So let us study each of these stages in detail. The first one is natural convection boiling, that is from to the point A, up to the point A on the boiling curve, that is here at the lower T excess, where T excess is about, delta T excess is about 3 degrees centigrade. So we do not see any bubble formation on the heating surface until the liquid is heated a few degrees above the saturation, that is 2 to 6 degrees centigrade, let's say, for water, and the liquid is slightly superheated in this case, and evaporates when it rises to the free surface. So it's like the liquid is slightly superheated, but it starts on evaporating as it goes into the free surface. And the fluid motion is governed by natural convection current. So inside there is all natural convection currents. Higher temperature fluid rises above, and at the free surface there is some evaporation. Heat transfer from the heating surface to the fluid is by natural convection in this case. Let us now discuss each stage in boiling in detail, and we will refer the boiling curve or the phase change curve for our reference. So as you can see, this is the first stage where the excess temperature, that is the difference between the surface temperature and the saturation temperature, is low, about 1 to 5. In that case, we see that the heat flux goes on increasing. This is referred to as natural convection boiling, and in this the first bubbles start forming, and this is at the point A of the boiling curve, and at various preferential sites on the heating surface there are some bubbles formed depending upon randomly spaced sites. The bubbles which form at an increasing rate and they also increase in number of that is the sites at which bubbles are formed goes on increasing, and they move along the boiling curve towards the point C. So as we move towards the point C, the number of bubbles that are formed goes on increasing, as well as the sites at which bubbles are formed goes on increasing till the point C, at which the heat flux is highest, and also the Txs is going on increasing if when we move ahead on the boiling curve, and this is referred to as nucleate boiling regimes. So let us divide this into two regions, that is point A to B and point B to C. So in the region between point A to B, we have isolated bubbles which are formed at various preferential nucleation sites on the heated surface. After that, these bubbles are dissipated in the liquid shortly after they separate from the surface. So there is bubbles form, they get separated, and they get dissipated in the liquid. The space that is vacated by the rising bubbles is again filled by the liquid which is near the heater's surface, and this process is repeated. So the process basically that happens is there is bubble formation at random preferential locations, and they separate from the surface, they rise in the liquid, and the region that is vacated because of separation of the bubbles is basically filled by liquid again. Now as we move into the region B to C, there is the heat flux increases as well as the Txs is increased. In this case, the heater temperature is further increased from 10 to 30. There are numerous continuous columns of vapor in the liquid in this case, so lots of sites are there where bubbles are formed. They actually merge together and form sort of a column of vapor in the liquid. These bubbles move all the way up to the free surface now, and they break up and release their vapor content. So the boiling is sort of accelerated now, and the nucleate boiling is the most desirable boiling regime, as we know, and also higher rate of heat transfer can be achieved in this regime with relatively smaller Txs. So the temperature required to get a higher heat flux is less. So even with smaller Txs like 30, we get highest flux in this particular point C, which is the maximum critical heat flux. This is also referred to as bubble collapse in the liquid in this particular region from A to B. And Txs is typically under 30 for water. In this particular region, there is nucleate boiling. Now once the nucleate boiling is complete, we go into the region which is referred to as transition boiling. In this case, the heater temperature increases above the point C, and the Txs is now increased past the point C. So we are in this particular region. As you can see, there are vapor pockets or columns that are formed, and then the heat flux decreases in this particular region, and the reason for that is basically large fraction of the heater surface is covered by vapor film in this particular region, and this vapor film sort of acts as a insulation because there is lower conductivity of vapor relative to that of liquid. So the heat flux is drastically decreased from point C to D because the vapor itself is covering the surface, and it is sort of reducing the heat transfer. And both nucleate and film boiling partially occur in this particular region. So there is mixture of both boiling regimes, and nucleate boiling at point C is completely replaced by film boiling at point D. And this is unstable film boiling regime, and it is avoided in practice because there is not much heat flux that we can extract in this particular regime. Going ahead now, let us discuss film boiling, which is after the point D, and in this case the heater surface is completely covered by a continuous stable vapor film. So now there is no liquid in contact with this particular heater surface, and the point D where the heat flux reaches minimum is called as Leidenfrost point, and in this case of Leidenfrost point, it was named after the scientist C. Leidenfrost, who observed in 1756 that there is liquid droplets on a very hot surface jump around and slowly boil away. So he was actually the inventor of this particular, or the discoverer of this particular phenomenon. And here we see the minimum heat flux, after which the heat flux again goes on rising as we go on increasing the heater surface. So the point to note is that the heater surface is completely covered by a stable continuous vapor film in case of film boiling. A pictorial representation of nucleate boiling is shown here. You have random sites or preferential sites on which bubbles are formed. They detach from the heater surface, move into the liquid, they dissipate, go to the free surface and evaporate. And we have nucleate boiling, formation of bubbles. And after that we have transition boiling, where we have this particular surface which is covered by vapor column or vapor film, We don't have much heat transfer flux that we can extract in this particular region. After that, we have the film boiling, where the surface is completely covered by film. The heater surface is completely covered by a liquid, by a vapor film. So these are the three particular regimes. This is nucleate boiling, transition boiling, and film boiling. If you want to look at it in much more detail, nucleate boiling, formation of bubbles at preferential sites, detaching from the surface, rising into the liquid. Transition boiling, which is basically there is columns of liquids that are present there, and basically this is sort of a much more accelerated form of boiling. And then we have the film boiling, in which the surface itself is covered by a vapor film.